Dr. Grant is doing research and needs to find the half-life of a sample of bacteria to determine the effectiveness of a new antibiotic. The bacterial colony has an initial size of 1,340, and then in 134 minutes, the colony has reduced to a size of 9 because of the antibiotic. And we're supposed to use this information to find the half-life. Now, the half-life is when you have something, whether it's bacteria or a population of something, the half-life is the amount of time for that population to decrease down so that it's down to 50% of what it started with. So that's what we want to figure out. This formula that was given to us, this is an exponential model. The T represents time. The HL is the half-life. So that's what we're going to be solving for. And the A that's in front here, that's our initial value. You may see it labeled in other books with different variables, but whatever's in front there, no matter what the notation is, the number in front should be your initial value. So this model, what it does is I plug in the time and I would get out what's left after that period of time has passed. So we have that information here. We have the time, 134 minutes, it decreased to a size of 9. So I'm going to plug in 134 into T, and 9 is what happens, what we get out after 134 minutes. So that's going to go in for A of T, which is our dependent variable. And another way to write this that you may be more comfortable with is an ordered pair. I plug in 134 and I get out 9. Different ways to write it. Now we also have, let me put in a different color. We also have the initial value. That's the 1,340. That's what we're going to plug in for A. So we also have A is equal to 1340. So let's plug in all these values and then we're going to solve for the HL, which is our half-life. So what we're going to plug in for our A of T, we're going to plug in 9. We're going to plug in 1,340 for our initial value. And then for our time, we're plugging in 134 minutes over our half-life. And that half-life is what we're trying to find. Now, when you're trying to find something that is located in an exponent, the only way that you can do that by hand is to use logarithms. And so what we need to do in order to solve an exponential equation with logarithms, the first step is to get the exponential part of the equation by itself. So the first step is to get this part, that's the exponential part, it's the base with the exponent, to get that by itself. So to do that, I'm going to divide both sides of the equation by 1,340. And then on this side, I'm left with 1/2 raised to the power of 134 over our half-life. Okay, now we have it set up where the exponential part is by itself, and we can take the log of both sides. Now, it doesn't matter which log you use, no matter what the base is. You just have to be consistent in whatever base you pick. You have to do it to both sides. I'm just going to use regular common log, which is base 10. I'm going to take the log of both sides. So I'm going to take the log of both sides, and that on the right side I get 1/2 log of 1/2 of 134 over half-life. Now the reason that we do this is because there's properties of logarithms that are very helpful. One of the properties of logarithms says if you have a log and your argument raised to an exponent, you can bring that exponent down in front. And by pulling that down in front, we get that HL, the half-life, out of the exponent so that we can solve for it. So I'm going to take this exponent and bring it down in front. I'm just going to bring everything else down as it is. I'm only changing the exponent and bringing it down in front. So now we have 134 over HL times the log of 1/2. Okay, now to solve for HL now, we have it in the denominator. So what we can do is we can multiply both sides by HL, and that will get rid of it in the denominator. So I'm going to take my half-life and multiply it on both sides. And that way, when I multiply it on the right-hand side, this HL is going to cancel out because you have the HL in the numerator and the denominator, so you can just get rid of it. So what I'm left with now is 134 times log of 1/2. And then the last step, we want to get the HL by itself. That's what we're solving for. We can divide both sides by the log of 9 over 1340. Now I know this seems a little bit weird if you're not used to using logarithms, but this logarithm is just a number. We don't know what it is offhand unless you're a walking calculator, but it's just a number. Who knows what it is? We'll plug it in later and figure it out. But if I had some number times x is equal to another number, to solve for that x, we would have to divide both sides by what's in front of the x. And that's exactly what we're doing here. We're dividing both sides by this log so that we can get the HL by itself. So what we're left with is that HL is equal to 134 times log of 1/2 and then divided by log of 9 over 1,340. Now we need to put this in decimal format, and keep in mind that you don't want to round intermediate steps, because if you keep rounding every step, then it's going to throw your answer off quite a bit. You only want to wait till the end to round. So we're going to wait and put this whole expression in our calculator and then get the decimal value one time. I'm going to put in, let me go up a little bit so we can see it, 134 times. Now to find your log, you have to hit the function button. That's this fx right here. So we're going to use log, which is common log is base 10. And then I'm going to put in 1/2. So I'm going to go back to my numbers. So 1 divided by 2. And then that's what's in the numerator. So then I'm going to divide by log. Let's see, go back to your functions, choose log, and then inside there, we're going to use 9 divided by 1340. Now this 134 is showing off to the side. That's the same thing as having it in the numerator, but if you're not comfortable like that and you want to make sure it looks exactly like what you did in your scratch work, start with the parentheses. So we would have 134 times log of 1/2. So then I want to come over and divide the log of 9 divided by 1,340. There we go. So according to our GeoGebra calculator, our answer is going to be 18.56446. Now the question says to round to the nearest minute, so we just want a whole number. So our final answer when we round that would be 19 minutes. So that means the half-life of this bacteria, when it's exposed to the antibiotic, has a half-life of 19 minutes. So that means if we start with 1,340 bacteria in 19 minutes, I'm going to have half of that. So that would be 670. Our final answer is 19 minutes.